Welcome to Summarize Science, where we dive into the latest breakthroughs in artificial intelligence and computer vision. Imagine wearing a pair of lightweight smart glasses, like the Project Aria glasses shown here, that can track your hand movements perfectly. While this sounds like a scene from a sci-fi movie, researchers have introduced a new framework called EgoForce to make it a reality. They focused on using a single monocular camera, which is significantly more difficult than using multiple sensors or depth cameras. Most current systems struggle to understand exactly where your hand is in 3D space because a single camera lens lacks natural depth perception. This depth-scale ambiguity means the AI might see your hand but cannot tell if it is small and close or large and far away. Furthermore, extreme distortions from wide-angle lenses used in VR headsets often make the math behind tracking very messy. To solve these problems, the researchers realized that the user's forearm provides a massive, reliable clue for the AI to follow. By looking at the hand and forearm together, EgoForce can use the known proportions of the human body to estimate the distance. They call this the hand-arm latent shape and orientation architecture, or HALO for short. This system uses a special transformer network to fuse information from the hand and the arm into a single 3D model. This approach allows the AI to use cross-attention, meaning it checks what the arm is doing to better understand what the hand is doing. One of the most technically impressive parts of this paper is the ray space solver. Instead of just guessing coordinates on a flat 2D screen, they project hand movements onto 3D rays extending from the camera. This allows the system to remain accurate across many different types of lenses, from standard perspectives to extreme fisheye views. Because the solver uses the camera's specific calibration, it works perfectly without needing a complete software redesign for every new device. The researchers also created a way to handle moments when the user's arm goes out of the camera's field of view. They used a variational prior, which allows the AI to imagine a plausible arm position based entirely on the hand's current orientation. This keeps the 3D skeleton stable even during complex tasks, where parts of the arm might be hidden by objects or the camera's edge. This prevents the jumping or jitter often seen in older VR tracking systems when a limb is partially obscured. In their experiments, this method significantly outperformed several other state-of-the-art AI models. On challenging benchmarks like the HOT 3D dataset, they managed to reduce tracking errors by a staggering 28%. The system also showed great temporal stability, meaning the movements look smooth and natural over time rather than shaky. You can see here how the AI projects a virtual 3D mesh over real-world video with incredible precision across different datasets. It handles difficult scenarios like motion blur and hand-on-object occlusions that typically cause other systems to fail. The entire pipeline is fast enough to run in real time, making it practical for actual use in consumer electronics. To summarize, the researchers have found a way to use the forearm as a geometric guide to solve the one-camera depth problem. Their ray space solver makes the technology universal, allowing it to work with almost any lens configuration imaginable. This means the future of AR and VR glasses could be much lighter and more comfortable because they will require fewer sensors. We are quickly moving toward a world where digital interactions feel just as physical and precise as the real thing. Thank you for joining us for this update on the future of spatial computing here on Summarize Science.